Hey everyone, welcome back to Calculus 2. This will be lecture 11 of the course, and in this one we're going to continue with our exploration of volume. And previously we discussed the disk method, and otherwise known as the disk and washer method, and we discussed that one previously. What we're going to talk about this time is kind of an alternative method but similar in setup, and it's called the shell method. Okay, so it's going to share a lot of the same characteristics as the disk method, i.e. we're going to be using a single integral to calculate a volume, and it's going to involve calculating the volume of solids of revolution. There's going to be an axis of revolution, but it's just going to be a different type of construction. The construction will be quite a bit different, but similar in feel. Okay, so let's jump into that, and we'll call this section 2.3. This will be 2.3, the shell method, right? Volume, the shell method. Okay. All right. So, as I said, this is an alternative to the disk method that we discussed previously. Now, there are going to be instances where the two methods are more or less interchangeable, right? You should get the same answer with both methods, and very often you can use one or the other at your discretion. There are going to be some instances where one would be preferred to the other, simply because of the setup of the problem, or the particular shape that you're looking at, and we'll discuss that a little bit. But before we get in, of course, let's just talk through what the heck is the shell method all about. Okay, so we're going to start with a rectangle. Okay, and so you're going to have this rectangle. It's going to have a certain height. Okay, and I realize I've drawn it on its side, but that's okay. It's also going to have a particular width. Okay, and this rectangle is going to be rotated about an axis of revolution that is that runs parallel to it. Okay, so in this case the rectangle is oriented horizontally, and the axis of revolution, it would also be horizontal. Okay, so we can imagine what would happen if we were to rotate this. It would kind of look a bit like this, right? It would come down, right, and you'd get some kind of a cylindrical shape here. Okay. Right, so it would look a bit like this, wouldn't it? Right, you'd have kind of a thing behind it there. Okay. Right, so we can picture this. Okay, so it's this longer rectangle. It's rotating around this axis of revolution here, and so it's called the shell method because you create a shell like this. Okay, so this sort of hollow cylindrical object is called a shell. Okay, that's what we mean by the word shell. Okay, so keep in mind here, so far we've got h is the height, w is the width. Now we want to introduce another quantity, and that's going to be p. Okay, now p is going to be the distance between the axis and the center of the rectangle, right? So if this is where the center of the face here, then p is going to be the distance up to the center of the shell. Okay, so let's take this this face of it here and kind of break it down. Well, let me write this in here. So p would be the distance between the axis and the center of the rectangle. Okay. All right. Okay, so hopefully we can see that. Now let's take this same picture, and we're just going to kind of reorient this face so that it's right, kind of in front of us here. Okay, so here you go. This is the cross-sectional view of the shell. Right, so take the face here. So the axis of rotation, of course, is going to come directly out of the center of this thing. Okay, and so we just said that this is going to be P, the distance from the center of the shell out to the center of the rectangle. Okay. Now we're going to define two other radii. This is kind of like the radius. We're going to just define two additional radii. The first one is going to be kind of the inner radius. Okay, and I'll just call that r of I. Right, so that's of course the distance from the center, i.e. the axis of rotation, to the inside edge of the rectangle, right, the near edge of the rectangle. And then we can also define the outer radius. We'll just call that RO. That's the outer radius. And that's going to be, of course, the distance from the center, i.e. the axis of revolution, to the edge, the outer edge of the rectangle. Okay, so you've got two pieces here. You've got R of I, which is the inner radius. Now what is that in terms of P? Well, remember this width here. This is the W, right? Right, the width of the shell is W. So the inner radius is always going to be equal to P minus W over 2. Okay, some distance to the middle of the rectangle minus half the width of the rectangle. Okay, minus W over 2. And then RO, that's going to be the outer radius. That's equal to P plus W over 2, isn't it? Right, P is, from the center to the center of the rectangle, but we need to go a little bit further. We need to go half the width of the rectangle. So that's the plus W over 2. Okay, so we can identify the volume of this cylinder using these quantities. Okay, so it's going to be based on, the volume will be based on the formula we previously saw, and that's just pi r squared times the height, right? And just like before, we're going to identify two separate volumes. We're going to first identify the total volume, including the interior piece, the total volume including the interior piece, and then we're going to subtract from that the volume of the interior piece that's not included in the shell. Okay, so we can do that using basically the volume of the entirety would be pi times the radius squared, where here the radius would be the outer radius. So I'll write R of O, okay, and then of course times the height. This is going to give us the total volume. And we want to subtract from that the interior volume, right? The interior part of the cylinder. And that's going to be equal to pi times the inner radius squared times the height, right? Okay, and this would be the interior volume. And of course, when I subtract the interior volume from the total volume, I get the volume of the shell. Okay, no problem. Right, so that's the idea there. Now, let's go ahead and work on this formula here, because this is the basic setup. Let's go ahead and work on this a second. So the outer radius and the inner radius are better expressed using these P minus W over 2, P plus W over 2. So let's rewrite them using that. So pi times the outer radius was P plus W over 2. We got to square that, times the height, minus pi times the inner radius, which is P minus W over 2. Square that, times the height in both cases. Okay, let's go ahead and pull the pi and the h out of here. So you get pi times h. And then inside you've got P plus W over 2 squared minus P minus W over 2 squared. Okay, and we can pretty easily expand this and simplify a bunch. So let's just do that. So when we expand this one, p plus w over 2 squared, we get, p squared plus pw plus w squared over 4. That's just foiling this piece out. Okay, and then we do the same thing here, and we would get p squared minus pw, and then plus w squared over 4. Okay. All right, and then, of course, we can combine terms here. And so you'll notice here that a bunch of things drop out. The p squared minus p squared goes away. And then here you've got pw plus pw, and then the w squared over 4 minus w squared over 4, that goes away. And so what you end up with here is pi times h on the outside, and then basically pw minus negative pw, so basically 2pw. Okay. And so this piece here, this is, you can write it a little bit better if you put it like this: 2 pi times p h w. And what are these things? Well, okay, let's remind ourselves. P is the radius, the average radius. Why do we say the average radius? Well, there are two radiuses, right? There's the inner radius and the outer radius, and p is right in the middle of those two, right? So if you take this number, whatever it happens to be, plus this number, whatever it happens to be, divide by 2, you get p every time, right? So it's the average radius. Okay. Oh, it's also the radius to the center of the shell. You can think of it in that way if you prefer. H is the height of the shell, and W is the width of the shell. Okay, so this is the basic setup. This is what we're going to use to derive this volume formula. So this can be used to find the volume of a solid of revolution. Okay, so this is the sort of the big starting point for the shell method. Okay. Let's talk through it in a little bit more detail. Let's break down a few other items here. Okay, so let's say we have some kind of a figure in the plane, planar figure here, in this case a triangle, and we've got it's inside of some kind of coordinate system here. Okay, and let's just say that our rotation is going to be along this axis, the x-axis, I guess. And let's just put some figures on here. That's C up to D. Okay, we're going to have representative rectangle that runs parallel to the axis of rotation. And that means that the width of this thing will be a dy, a delta y. Okay. And the distance, the average radius will be calculated as a function of y. Okay. And then, of course, the height here, right? This is our h of y. Is that piece. Okay. Okay. So the volume is going to be equal to 2 pi times p of y, h of y, times the width, which is going to be delta y. We'll hold that constant for all of the rectangles. Okay. All right, so you can imagine we create more and more rectangles, and of course this is rotating. That's the 2 pi piece of it. This is rotating about this axis and creating a solid three-dimensional figure, three-dimensional object. Right, so we can approximate the volume of the solid by n such shells. Okay. Each of them will have the same thickness, delta y. Okay. height HYI. Right, the height function is going to vary depending on the shell, obviously. And the average radius will also vary a bit depending on the shell, right? The distance from the axis, so some will be closer, some will be further away. Okay. Okay, so that's the idea. So if we were to take n of these, right, shells, how would we sum them up? How could we write this? So we'd say the volume is approximately equal to the sum, I equals 1 to n, so n different shells. And then we're going to have that 2 pi in there. Okay, and then we'll have a p of yi times an h of yi times a delta y. Okay, and so just to write that slightly different, so it'd be 2 pi times the sum I equals 1 to n p of yi h of yi delta y. Okay, so this is going to approximate the volume. Now obviously the more shells you have, the closer the approximation. If I have 3 shells, it's going to be a pretty bad approximation. If I have 3,000 shells, it's going to be a pretty darn good approximation. But now what's going to happen is, you know, this is calculus, right? So what we're interested in is what happens when the number of shells grows without bound. Increase the volume of, the number of shells increases without bound, then what happens to the volume approximation? Well, as n goes to infinity, or, you know, you could say as the norm of the partition goes to 0, right? The approximation becomes precise. Okay, so the approximation becomes precise, and so what we would say then is that the volume is equal to the limit as the norm of the partition goes to 0 of the sum, don't forget the 2 pi in there, I equals 1 to n of p of yi h of yi delta y. Right, so the volume would be equal to this, which is the integral 2 pi times the integral from c to d of p of y h of y dy. All right, so it's basically the same story as what we saw with the disk and washer method. It's just the construction's a little different, right? In the disk method, we had a pi times the integral of r squared. Right here, we've got 2 pi times the integral of p times h. So you can see that's just a different way to find the area, right? But it's using the same principles. Okay. So we've kind of been talking about just the horizontal setup. All right, so let's just recap that. All right, so if you have a horizontal axis of rotation, then that's what we've been describing, isn't it? Right, that's where you're going to have, you know, some shape. Your representative rectangles are going to be parallel to the axis of rotation. All right, so if this is x and this is y, then you're going to have an hy, you're going to have a p of y, and you're going to have delta y's, right? And so the volume would be 2 pi times the integral from c to d of py, hy, dy. Okay. In the case of the vertical, axis of rotation, sorry, start writing too fast. In the case of the vertical axis of rotation, right there we're spinning around the y-axis. Okay, So remember, the thing that kind of one of the things that differentiates this from the disk method is that the representative rectangles here are parallel to the axis of rotation. That was exactly the reverse with the disk method. Right, so here, if we're spinning around the y-axis, that means we're going to have vertical rectangles, right? And so that means we've got delta x width, we've got h of x height, and we've got p of x radius. Okay, so the volume would be 2 pi. In this case, it would be a to b of p of x, h of x, h of x dx. Okay, but basically the same setup, just swap out the y's for the x's. Okay. But I think it's important to have these schematics in your mind. You know, especially like it helps you to remember which direction the integration is, and you know where is the radius function coming from, where is the height function, what's it all based on, right? So having these kind of schematics in mind is helpful. Okay, but I mean, the integral is straightforward, right? It's just swapping out y's for x's, obviously. So let's do an example here and see how this works in practice. Okay, so we're going to say find the volume of the solid of revolution formed by revolving the region bounded by the function here is y equals x minus x cubed, and the x-axis 0 less than or equal to x less than or equal to 1 about the y-axis. All right, so we've got this function y equals x minus x to the third power, and it's going to it and the x-axis are going to define a region, and we're going to spin that region around the y-axis. We just want to know the volume of the resulting solid of revolution. Okay, so let's plot the function first so we can do some visualization here. Okay, so I got my x-axis, my y-axis. So this is y equals x minus x to the third power, and we're specifically interested in this between 0 and 1. Okay, so if you go out to Wolfram Alpha or you pull out your graphing calculator, you can plot this, and it's going to look something like this. It kind of comes up and goes down, right? And in specifically on the interval from 0 over to 1. Okay, so this is y equals x minus x to the third power. Okay, now it does say we're going to rotate this around the y-axis. Okay, so it's going to look like that. And so that means our representative rectangles are going to be vertical in this case, right? So we'll have some height for each of the shells, and that's going to be basically the function, right? So you'll have your h. The width is going to be determined as delta x, right? So that's the width. And then here's the question, like, what do we call this distance? What's our p function? So what's p of x? So how far away from the axis of rotation is each of the radii going to indicate? Well, it's just x, isn't it? Right? So however far this happens to be, it's just going to have a value x. Okay, so the average radius function p here is just x, and that's going to be true in a lot of cases, nearly all of them. Okay. All right, so we've got all of our pieces. So I think we can set up our integral now. So the volume is going to be equal to 2 pi times the integral from a to b of p of x, h of x, dx, right? And so what are all of these pieces? Well, the a is, so we're going to integrate from 0 up to 1. So to be the integral from 0 to 1. P of x, we say, is just x. Right, it's going to tell us the average, the radius, the distance of the average radius of the shell. And then h of x is this function right here. And so that's going to be x minus x to the third power. So that's a very straightforward integrand to deal with there, right? So we can just do this quickly. So I would just recommend turning this into a polynomial, x squared minus x to the fourth power. Okay. And so then the integral is just 2 pi, and it's x to the third over 3 minus x to the fifth over 5 from 0 to 1. So what do we get? We get 2 pi times a third minus a fifth. All right. And of course that's also minus, the lower bound too. Let's not forget that. So it'd be minus 0 minus 0. Okay, so altogether here we get 2 pi, and then it's 5 minus 3 over 15. And so I believe you get 4 pi over 15, right? So 2 times 2 is 4. Okay. So that is basically, that's the volume. This is going to be the volume of this thing here as it spins around the y-axis. Okay, great. So that's a nice example. Let's do another one. It was a pretty straightforward example. So let's try another one. So I will write this all out. So find the volume of the solid find the volume of the solid of revolution formed by revolving the region bounded by y equals e to the negative y squared and the x-axis 0 less than or equal to y less than or equal to 1, and the y-axis, sorry. And we're going to spin this about the x-axis. Okay, so there's the example. So find the volume of the solid of revolution formed by revolving the region bounded by y equals e to the negative y squared and the y-axis about the x-axis. Okay, so let's plot this. Always plot them first. All right, you guys see what these things look like. Okay, so if we're doing so this should be, I'm sorry, I think this should say x equals, sorry, typo there. So x equals, right, so if we were to plot x equals negative y squared on this graph, it would look something like this. Okay, so this is your x-axis. This is your y-axis. Okay, now we'll say this is 1, and then of course this is 0. So the region here is from 0 to 1, so it's basically this right here, and we're going to spin it around the x-axis. All right, and so if it's spinning around the x-axis and we're using the shell method, then we're going to have representative rectangles that look like this. Okay, and we can quickly see what all of the pieces are. So p of y will be just equal to y. We'll have an h of y here, right? That's going to be the height. We'll have a delta y. So the height, what is the height? Well, the height is just this function, e to the negative y squared. Okay, so h of y equals e to the negative y squared. It's the height of the rectangles. Right, so if you plot the thing, if you plot the the region, and you put the rectangles in and you just label the parts, it's not that you can't mess it up. It becomes much more difficult to mess up though. If you actually are looking at this and you say, oh yes, this is definitely y, and that's definitely, from here up to that, That is definitely e to the negative y squared. It's obviously a delta y since we can be integrating across the y-axis. So, you know, I highly recommend to people who are learning this for the first time to just plot the thing. You know, bite the bullet and just plot the plot the region. Unfortunately, you have to pretty much every time. All right, so then we can set up our integral. So let's write down sort of the formula for this. It would be 2 pi times the integral from c to d of py hy dy. And so that means it is, so what is the region? It's 0 up to 1. It's given. Our py we see is y, and our hy is e to the negative y squared. Okay, so this is what our integral looks like. Okay, can we integrate this? Yeah, we definitely can integrate this. What we're going to do is we're going to use a u substitution, so just kind of off to the side. Come in here and say u is equal to negative y squared. So that means du is equal to negative 2y dy. And so we have the y here, right? But we will have to move the negative 2 over. And so that means du over negative 2 will be equal to y dy. And so this is just kind of, depending on how you're calculating this integral, you may need to work out the change of variables. And so when you do that, though, you get 2 pi times the integral from 0 to 1 of e to the u over negative 2 du. Okay, so the du over negative 2, that's here. That's this part. Substitute that in for y dy. And then the negative y squared becomes just u. Okay, so you got that. All right, so the negative 2 and the pi cancel. Well, we'll just leave it in there for now. So if we integrate this, I'm going to put it down here. If we do this integral, you'll have 2 pi on the outside, and you know what do you get here? You get negative 1/2, and then it's just e to the u, right? And that's from 0 up to 1. And so technically this is y equals 0 up to y equals 1. So you're going to be a little bit careful since you're doing change of variables here. And so that's equal to, the cancellation happens here. You get negative pi times the integral e to the negative y squared, and that's from 0 up to 1. And so negative pi times, so e to the negative 1 squared would just be 1 over e, and then e to the negative 0 would be just 1, so minus 1 there, right? And let's see, so that's going to be equal to negative, oh sorry, we can factor a negative out and just make this pi on the outside, and then it'll be 1 minus 1 over e. Sorry about that. 1 minus 1 over e. And so, you know, that's a hard number to visualize, so let's just plug it in, see what it's worth. So it's about 1.986. Okay. So that's the volume of this region if it's revolved around the x-axis. Okay. All right, so two pretty good, pretty reasonable explanations or examples of using the shell method. And let's talk next about, let's compare the shell method to the disk method. So they obviously vary. Let's just refresh our memories on exactly how they vary and what that means. So let's do a comparison. Comparison of disk and shell methods. So let's recap the disk method here. Okay, so the disk method, here's the setup. All right, we've got some region. Okay, you got your x-axis and your y-axis. Right, and if the axis of rotation is vertical, right? Meaning we're going to spin around y. Then what that meant was we would have a basically a representative rectangle that was perpendicular to the axis, right? So in the case of a vertical axis of revolution, that meant horizontal representative rectangles, and so that meant you would have a delta y here. You would have an outer radius, which is this distance. You would have an inner radius, which is this distance, right? And then the integral basically was v equals pi times the integral. In the case of integrating across the y-axis, it's common to use c and d as your bounds, and so it was r squared, big R squared, outer radius, minus inner radius, and it was with respect to y. So that was the setup with the disk method in the vertical orientation. What happens if we switch it to horizontal, right? So same function, right? This time we're going to rotate around the x-axis, right? So that means we're going to have vertical rectangles, okay? And that means we get a delta x width. It means our outer radius is, typically the function of x. Our inner radius is also a function of x. We've got our bounds a to b, so I didn't put c to d on here, but I'll write that. Right, so it's basically the same thing, just kind of flipped, right? And so here the volume is equal to pi times the integral from a to b of, again, r squared minus little r squared, integrating across the x-axis, okay, dx. So, obviously the formulas are going to vary with the shell method, but I'd say the biggest differences between shell and disk methods are, one, obviously the formulation, the integrand itself, and two, the representative rectangles are flipped. Right, so they're flipped. So here, the representative rectangles were perpendicular to the axis of rotation. In the shell method, they're parallel to the axis of rotation. Okay, so let's just recap. So on the shell method, all right, you had the vertical setup. Okay, so same picture. So rotating again around the y-axis. So with the shell method, we had vertical, right? We had the vertical representative rectangles. That means we're going to have a delta x width. We're going to have an h. That's a function of y. And we're going to have, it's a function of x, and we're going to have a p is also a function of x. Okay, so the volume here was equal to the integral from a to b. Don't forget the 2 pi. And then it's p times h dx. Okay, so remember, it's exactly the opposite, right? So here you're integrating with respect to y. In the shell method, you're integrating with respect to x. Okay, and then horizontally, similar, right? So here we're going to rotate around the x-axis. Okay, and so that means our representative rectangles are going to be parallel to the x-axis, right? So that gives us a delta y. We're going to have some h function, which is a function of y, and we're going to have some p function, which tells us the average radius from the center of the shell, right? It's going to be basically the radius from the center of the shell to the axis of rotation. And that's also going to be a function of y. Okay. Right, so if you have a region C to D, then the volume there would be 2 pi times the integral from C to D of P times H dy. All right. So these are totally different. But you can see they're obviously like similar in spirit, right? Just the construction, as I said at the onset, the constructions are different here. This is the disk method. This is the shell method. But it's really just a matter of kind of flipping the way the representative rectangles are oriented with regard to the axis of rotation. That's sort of the big piece, right? The sort of structural difference between the two. And then, of course, that is going to bleed into how the integrand itself is structured, right? So here you've got a P times H. Up here you've got a outer radius squared minus inner radius squared, right? So that all is consequence of kind of orientating the representative rectangles differently with respect to the axis of rotation. Okay, very good. Now I know that's a lot to know, a lot to remember, so you can just kind of, what I would recommend is just take really good notes on that, have good examples that you can use to look at if you're taking tests or something on this. So what I want to take a look at is an example that we previously looked at. We looked at when we were learning the disk method. And we ran this example through the disk method and it was fine. But I want to see, like, how does it vary? How does the calculation vary when we run it through the shell method? So let me write the example problem down, the problem statement here. So we want to find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. All right. So remember this is an example we did in the previous one. Let's plot this. Let's figure out what this region looks like. Okay, so we've got y equals x squared plus 1. Okay, so if this is 1 and that is 2, and let's just kind of blow it out a little bit on the x-axis, then this is going to look like kind of like this. Okay, this is your y equals x squared plus 1. That's this piece. It's a function, right? So just a quadratic function, so we know what that looks like. Shifted up 1 unit. And we're interested in the region bounded by this function, y equals 0, x equals 0, and x equals 1. And so we can see that that's just this piece here. Okay. And then we're going to rotate this around the y-axis. Okay. All right, so and so when we looked at this one previously, we saw that there were two regions where the rate. So remember, it's with the disk method, it's all about the inner radius and the outer radius. So let's just actually write this down here. So disk method. All right, so the volume in this case is going to be equal to pi times the integral, and it's c to d since we're rotating around the vertical axis, and it's going to be basically r of y squared minus little r of y squared dy. That's kind of the formula for the disk method. And so r is a function of y, both of them are functions of y, and we see that basically what ended up happening right, was that if you have a representative rectangle up here, then your inner radius is going to be different than a representative rectangle located down in this section of the region. Right, so up here, sorry, down here, the inner radius is 0, right, because the rectangles are butted right up against the axis of rotation, the y-axis. But up here, the inner radius is this function here. It's this curve, isn't it? Okay, so we'll kind of call this, so this part here we called region 1, and this part here we called region 2. Let me double check that. Yeah, sorry, this was region 2, this was region 1. Okay. So in region 1, our outer radius was just 1. Okay, right, you can see the outer radius is 1 actually across both regions, and the inner radius was 0. In region 2, the outer radius was again still 1, and the inner radius here was different, right? So it's this curve up here. And so what we can kind of just do a little bit of work on this, make this x as a function of y, and when we do that algebra, we see that that function would be y minus 1 square root. Okay, so you got these kind of two pieces, right? And because, you know, the inner radius varies depending on which region you're talking about, that means you're going to have two integrals. Okay, and so we can integrate this. So the first region, we'll just do region 1 to start with. That's going to be 0 up to 1, and it's going to be this squared minus this squared, big R squared minus little r squared. So it'll be 1 squared minus 0 squared. Okay, plus the second region, which would be 1 up to 2. And there again, it's going to be big R minus little r, both of them squared. So it'll be 1 squared minus square root of y minus 1 squared. Right, so you have these two integrals, right? This one being your region 1, this one being your region 2. Okay, and so we did, we did the calculation, and you can jump back to the prior video to see that. But basically, these integrals are straightforward, and when you run the numbers here, when you run the numbers, you get 3 pi over 2. All right, but you got to run the numbers. Okay. Okay, so how can this problem be addressed with the shell method differently? Okay, so this is the disk method. What about the shell method? Okay, so the shell method. Well, let's draw the picture again, this time probably with a little more haste. Okay, but okay, so we've got, again, same situation, rotating around the y-axis, right? So we've got this is 1, this is 2, and this is 1, and this is 0, right? And this is the region, and then we're rotating around the x-axis. So, sorry, around the y-axis. Same as above, right? Just kind of drawn differently. Now, if we're using the shell method, then the representative rectangles are parallel to the axis of rotation. That means they do this instead, right? And so using the shell method in this instance is preferable because you no longer have to concern yourself with this region 1, region 2 business, right? Here we had to have two separate integrals because of the inner radius varying across this interval. And so we don't have that problem with the shell method, do we? Right here, so what do we need with the shell method then? Well, we need, so since we have a vertical axis of rotation, that means our representative rectangles are vertical, which means we have a delta x width, we have an h of x height, and we're going to have a p of x equals x radius. Okay, So this is somewhat more straightforward of a setup. Right? Now, it's not always the case that the shell method is easier, but in this case it happens to be. It happens to be somewhat more straightforward. And so the integral here, remember, is 2 pi times the integral from a to b, and then it's p of x, h of x, dx. That's the formula. And so we can plug these quantities in. So from 0 up to 1, our p of x, right, that's just x. Our h of x, well, that's the function itself, so that's x squared plus 1. There we go. So we can do this really quickly. This will be x cubed plus x. All right. And so what do we get? We get x to the 4th over 4 plus x squared over 2 from 0 up to 1. And so the 0 will be nothing. Plugging in the 1, we get basically a 4th plus a half. All right, a 4th plus a half is, that's 3/4. And so we get, what, 3 pi over 2. Perfect, right? So it agrees. And they should, naturally, right? They should agree. Okay, so in that case, what did we see? We saw that the shell method is, it's not like you couldn't use the disk method. We obviously did use the disk method. It's not that much more work. But you can just see this is a good example of how the two methods vary and where it's possible that one could be more straightforward than the other. Right? I think, these are obviously relatively simple integrals, but it's more like kind of having to think through how the inner radius, outer radius, all of the various functions involved, how they relate to one another and the given region. All right, so there's some thought that has to go into it. What I recommend to people is get mega competent with at least one of these, disk method or shell method, and it might be possible for you to get to the point where you look at a region and a setup and just immediately can see that the method you're familiar with is a hard example, in which case it might be worth going to the other method. Or if you say, hey, I can quickly do this with the disk method, you don't have to worry about the shell method, or vice versa, right? So I myself tend to prefer the disk and washer method. I just find it a little bit more straightforward, a little quicker. But I'm versed in the shell method as well. So if I come across an integral where I need to do something, and it is in fact a lot easier with the shell method, I can do that, right? But it's not my default. My default is disk. But okay, so that's it for this section. And so disk and washer and shell method have now all been covered, and we'll continue next time with more applications of integration. See you then.